Hello everybody and welcome back to the course. So in the last session we developed a vectorized NumPy code that allowed us to determine the number of unique values in a one-dimensional array. And now we are getting serious because our solution must also work with many simulations. So technically speaking, in a two-dimensional space with matrices. So first of all, let's import NumPy as NP. And first of all, we again start with our toy example. So we roll the dice, and our dice has of course 6 pages, and we throw 6 times, and we do this 10 times. So simulations is 10, and we set the seed to 42. And then we are creating 10 times 6 random integers in range 1 to 6 including. So we are rolling the dice 6 times, and we're repeating the process 10 times. And reshaping this into a matrix with 10 rows. So we have 10 simulations and 6 columns. And we name it M, like a matrix. So now we have here a matrix with 10 rows and 6 columns. And for example, let's take here the second row. This is a simulation of 6 times rolling the dice. And we get 3, 3, 3, 5, 4, 3. So now we can sort our matrix row-wise. So we take the function npSort, pass our matrix and say axis equals 1. So we sorted each row in an ascending order. So now, for example, here our third row we have 2, 4, 5, 6, 6, 6. And as before in the one-dimensional case with only one simulations, now we make a slice and drop in the first slice the very first element, in the second slice in the very last element. But now we are not dropping an element, we are just dropping a column. So we are dropping the first column and the last column. And actually there's not too much we have to change. So this was the code in the one-dimensional space, and now we are saying, okay, we have our matrix. We want over all rows the first column excluding until the very last column including. And the second slice, we want to slice all rows from the very first column including until the very last column excluding. So let's see what we get. So we get 2 slices here. And here in the first slice, we dropped the first column here. So we are starting from the second column, 3, 3, 4, 2, 1, 3, 3, 4, 2, 1. And in the second slice, we just dropped the very last column here, 5, 6, 6, 5. So we have here at the end the second last column, 5, 4, 6, 4, 5, 4, 6, 4. So now what we can do, we can compare element-wise if the elements of the 2 slices are equal or not. And therefore, as before, we only have to make minor changes here. We have to include that we want to check it over all rows. And there we are getting a matrix with Boolean values. So let's check here the very first element. We have 3 and 2. They are not equal. So we get a true here because we checked here if the elements are not equal. Let's check here the second element in the first row, so 4 and 3. These are also not equal, so true. And NumPy checked it here for all elements, so checked element-wise if the elements are not equal. And what we can do now, we can take for each row the sum of all trues. So let's copy here the code. And then we take npSum. And then we have to define that we sum over all rows, so axis equals 1. So now we have here an array with the sum of all trues for each row. So let's see here the first row, we have 3 trues here. In the second row we have 2 trues, 2. In the third row we have 3 trues, 3, and so on. And last but not least, we have to add 1. So in order to get the number of unique values in our rows. So if you check here, so in the first row, we should have 4 unique values. Let's go back to the matrix. So we have 2, 3, 4, and 5. That's correct. And in the second row we have 3 unique values. 1, 2, and 3. So our code is correct and it works. And yeah, therefore then we can now go to our sticker album challenge, and we set again album capacity to 600, purchase stickers to 800, seed to 1 to 3. Simulations, let's start with 1000 simulations. Then we are creating 1000 times 800 random integers, so we are buying 1000 times 800 stickers in the range of 1 till 600. So we have 600 unique stickers, and we reshape it into a matrix with 1000 rows and 800 columns. And we assign the variable m, and we sort the matrix M row-wise. Okay, so we can check the shape here of M. So we have 1000 rows and 800 columns. And in order to determine the number of unique values, yeah, actually we can just here copy the code from our toy example and paste it. And let's see what we get here. So here we get an array with 1000 results. So we simulated the process of buying 800 stickers 1000 times. And we get 1000 results, how much unique stickers we get. So in the first simulation we get 439, in the second 444, and so on. Alright, so now we can further increase here the number of simulations, because I have the feeling that our code is quite fast. So let's increase it to 10,000. And now what we can do now, we can calculate summary statistics. Because now we have an array with 10,000 results, and yeah, actually we want to know what we can expect. So how many unique stickers we can expect in terms of the mean, or also the median, or maybe also percentile and so on. And yeah, this is much easier with NumPy, as NumPy has special so-called universal functions to calculate various statistics. So we can start here with the minimum. So we have the function npmin. We could also use the method results.min. So that gives us the same results. Okay, so first we have to assign here the variable results. Now we can also print it out one time. So now we can calculate the minimum of our results. It's 406. And also the maximum. It's 471. We can calculate the mean with np.mean. We could also apply the method results.mean. And we can also calculate the median. So the median is actually the value where we can expect that 50% of all results are lower than the median and 50% are higher. And we can also calculate the percentiles with np.percentile. So the percentiles indicate the value below which a given percentage of observations in a group fall. So for example, the 5th percentile is in the value below which 5% of the observations may be found. So in easy words, there's a chance of 95% that the value is higher than this, and on the other way, there's a risk of 5% that we end up with a value that is lower than the 5th percentile. So and in the np percentile function, we have to pass our array results, and we have to determine the percentile. So the percentile here is 5. And we get 429. And what we can also calculate is a prediction interval, which is actually simply a combination of a lower and an upper percentile. And for example, we take the interval 5 and 95, so we have the 5th and the 95th interval. And yeah, this gives us the range where we can expect our result in 90% of all cases. And in 5% of all cases, the result will be lower. And in 5% of all cases, the result will be higher. So in our case, the prediction interval from the 5th percentile until the 95th percentile is between 429 unique stickers and 455. So there's a 90% chance that we are ending up within this interval. Alright, so numbers are always good, but in the end, a graph should give us more information or more intuition on our results array. So we import matplotlib and set the style to seaborn. And then we can plot here our array with a histogram. So we pass our results array with 10,000 results. We set the number of bins equal to max minus min plus 1. And we call our histogram frequency distribution. Then we call the X label number of unique stickers, the Y label number of occurrences. And we also set a title. And let's see what we get here. So this already looks kind of bell-shaped, so we have 10,000 simulations, and as you can see here, we should actually expect unique stickers of in the range 440 to 450 about, and what we can also plot here in is a vertical line at the median. So 50% of all simulations end up at a lower value than the median and 50% at a higher value. And we can also plot a vertical line at the lower percentile. Here we have 5%. And also we can plot a vertical line at the higher percentile. Here we have 95%. So now we can see graphically that actually 90% of all occurrences or all simulations end up within this interval here. And there's a 5% risk that we end up at values below the 5th percentile, and there's a chance that we end up with results higher than the 95th percentile. Alright, so now we are finished with this session, and we were very successful. We found a vectorized code that also works with many simulations, and in the next session we go on and automate our code by writing a function. So hope to see you there. Bye.